In this part of the video, we're going to look at this new topic, new for AP Physics 2 in 2025, called the RC time constant. And we're first going to look at it at this situation right here in this simple series, where we've got a 12-volt battery, a 6,000 ohm resistor, a 100 microfarad capacitor, and two switches, S1 and S2. So here's what we'll do first. We'll close S1, and as we close S1, what that will do is that'll force a current that goes around in this direction. S2 is open, so there's no current going through S2. It's just going around this part of the circuit. So we do our normal thing with our VIR chart. This is a really simple setup. Remember, the capacitor right at the beginning at t equals 0 is acting like a wire. So the current's just flowing through right at the beginning at t equals 0. We take 12 and we divide it by 6,000 amps to get our 0.002 amps or 2 microamps. So eventually, we're going to get to a value of 12,000 microcoulombs in that capacitor. But that's gonna take a little while, okay? And the way we calculated that out is we use our QCV chart. We know that's a 1,000 microfarad capacitor. That's a property of the capacitor. That can't change. Why is this 12 volts? How do we know that's 12 volts? The reason for that is that we started off with a 12-volt capacitor, and as the current was going around, it charged up this capacitor to the maximum voltage that it can get to, which is 12 volts. Notice that the capacitor is in parallel with a 12-volt battery, so that's as high as it can get. So the time constant is actually not the entire time that it takes to go from 0 charge on the capacitor to 12,000 microcoulombs. The time constant is the time it takes to get to 63% of full charge, okay? The time constant is a convention used to determine certain properties of circuits, and that's how we calculate it, resistance times capacitance. Now, if we multiply the resistance, so what we say is this capacitor sees the 6,000 ohm resistance, and we multiply it times its own capacitance to get 0.60 seconds. Remember, that's not the total time it takes for this capacitor to get a fully charged to 12,000 microcoulombs. It's only 63% of that. So let's make some calculations. So it's going to take 0.60 seconds to get to the maximum voltage that it'll eventually have. So we take 0.63 or 63%, multiply it times 12 volts, and we end up with 7.56 volts. The total charge that we're going to get eventually is 1,200 microcoulombs. We multiply that times 0.63, and we get 756 microcoulombs at 0.60 seconds. All right. Now, if we graph it, notice here that the voltage is 7.56 volts, just like we calculated at 63%. And this vertical line is exactly at 0.60 seconds. Now, on our test, on the AP test, you don't have to draw this perfectly. You just have to know the shape, and you need to know some values at 63% and 37%. And I'll explain that more in class. All right. Now, for the current, so the current, remember, it started off at 2 microcoulomb, 2 microamps or 0.002 amps right when we turned it on, but then right when we turned on switch 1. But then as the charge builds up the capacitor, it decreases just like the voltage increased. All right. Um, Now we can calculate out that current at 0.37, and I'll explain in class why that's 37%. And so 0.37 of that 0.002 amps is 0.00075 amps. And you can tell it fits right there on your graph. Okay. All right. Now, at a long time after 0.60 seconds, this res, um, this capacitor is now at 12 volts. All right. So we've got 12 volts at that capacitor now. That happened again because this 12-volt battery is the maximum that this capacitor can become because it's in parallel with it. And so notice this is the positive side of the battery. That will cause positive charges on the same side of this capacitor as that battery and negative charges on the opposite side. Okay. All right, so now let's discharge the circuit. When we discharge the circuit, this capacitor, so let me back up a little bit. We're going to open up this S1 switch and we're going to close this S2 switch. What that does is it drains our battery. Now our battery has no more charge on it. So it's like this side of the circuit isn't even doesn't have a current. And now we've got a capacitor that's fully charged at 12 volts, and it's got these positive charges there and negative charges. And remember, the positive charges, they were going to go on this side of the battery. And now notice the current is going in this direction now, as opposed to before when it was going in this direction. Okay, so now it's going in this direction. So during discharge of the capacitor, the clock starts over. Okay, so it's like we start the clock over. Since we still got the same resistor and capacitor, the time constant is the same. All right, so what we'll notice here is that the time constant at 0.60 seconds, the voltage is 37% or 4.4 volts for the capacitor. Okay. And likewise, so that's the voltage, again, at the capacitor. All right. Now, for the current, I'll give you those values. The values are actually 0.60 seconds. So we multiply 0.37 times the total current, which was, again, 0.002 amps. And so now we're going to end up with 0.00075 amps. I'm sorry that my big old head is in the way there. Again, that's for the capacitor. And that's it.